In this video, we're going to talk about amino acids. Amino acids are the monomers of proteins. Each amino acid has a carboxylic acid functional group. It has an amino group, hence the word amino acid. It has a hydrogen, and it has an R group. This carbon is a chiral carbon because it has 4 different groups. Now, the R group describes the type of amino acid that you're dealing with. For instance, let's say if the R group was an isopropyl group. This particular amino acid would be considered a nonpolar amino acid because the R group is nonpolar. Bonds that are composed of carbon and hydrogen only are nonpolar bonds. So this would be considered a hydrophobic amino acid. This portion doesn't like to mix with water. So that would be an example of a nonpolar amino acid. Now here's another example. By the way, the one that I drew was called a valine. This is a polar amino acid because the functional group has a polar hydroxyl group. This particular amino acid is known as serine, and it has the abbreviation SER. Here is another one. This amino acid is called aspartic acid. Because of the acidic functional group, it has an acidic R group, so this is one of the acidic amino acids. The carboxylic acid functional group is also polar, so it's both acidic and polar. Now there are some other amino acids that you need to be familiar with. Another one is phenylalanine. So this amino acid has an aromatic ring, so it's considered to be an aromatic amino acid. Now, because the R group is completely made up of hydrocarbons, or carbon and hydrogen bonds, this is also a nonpolar amino acid. Now, there's one more type of amino acid that I want to go over, and this particular amino acid is called lysine. This one has an amine group, and it's one of the basic amino acids. Basic in terms of like alkaline, not acidic. So that's a basic amino acid. So keep in mind, this is the carboxylic acid group of the amino acid, and this is the amino group. So whenever you have a carbon atom that has an amino group and a carboxylic acid functional group attached to it, it's an amino acid. Now let's talk about the bonding that's found in an amino acid. Let's call that R1. So I'm going to draw out the carboxylic acid functional group. So this is going to be R2. That's the side chain for the second amino acid. Now, when two amino acids react, a dehydration synthesis reaction will occur. Water will be removed as a byproduct. And the result is going to be the formation of a peptide bond, which I'm going to show you shortly. So connecting the carbonyl group with the amino group, we're going to get an amide functional group, as you can see here. So that amide functional group, this is the peptide bond. So proteins, which consist of many amino acid residues, have plenty of this covalent bond, this peptide bond, which is based on an amide functional group. So that's the basics of amino acids. That's how they react to form polymers such as proteins. Now, here's a question for you. So I'm going to draw the structure of alanine. Alanine has the chiral carbon, a methyl group, a hydrogen, the amino group, and a carboxylic acid functional group. The pKa of the carboxylic acid part of the amino acid is close to 2. For alanine is about 2.3. And the pKa of the amino group is about 9.7. So with this information, what form will the amino acid be, let's say at a pH of 5? What is the predominant form? How would you answer a question like this? What I like to do is create a number line. Let me draw it over here. And the first thing I like to do is list the pKa's on the number line. There's only 2 of them, so 2.3 and 9.7. And then I like to draw the structure of the amino acids on the left, in the middle, and on the right. Now all the way to the left, both functional groups will be fully protonated. So at a pH of less than 2.3, the amino group will have 3 hydrogen atoms, and the carboxylic acid will be the way it is. So when the pH is less than the pKa, the carboxylic acid is protonated. But when the pH is above 2.3, this hydrogen will be removed. So we're going to get this form. The amino group will still be protonated, but the carboxylic acid is going to lose the hydrogen because we passed its pKa value. So notice that we have both a positive charge and a negative charge on this amino acid. So overall, the net charge is 0. This is called a Zwitter ion, where you have a positive charge and a negative charge in the same particle, but overall it's neutral. So that is the Zwitter ion of alanine. Now above 9.7, the amino group is going to lose a hydrogen. So this is going to be the structure of alanine. So the net charge when it's less than 2.3 is positive 1. When the pH is between 2.3 and 9.7, the net charge is 0. And beyond 9.7, the net charge is negative 1. So notice that under acidic conditions, the amino acid typically have a positive charge. And under basic conditions, amino acids typically have a negative charge. Now let's label this structure as structure A, structure B, and structure C. When the pH is equal to the pKa, you're going to have equal amounts of the protonated form and the deprotonated form. Since 2.3 separates structure A and B, at a pH of 2.3, you're going to have 50% of A and 50% of B. So the acid and the base will be in equal amounts. Now, when the pH is less than 2.3, structure A will be more dominant than structure B. So if you go down 1 unit, let's say at 1.3, the ratio between A to B is going to be 10 to 1. So approximately, you could say 91%, if you round it, will be structure A at a pH of 1.3, and about 9% will be structure B. Now, if we go 1 unit further, let's say at 0.3, the ratio between A and B is going to be 100 to 1. So about 99%, or rather 99.1% will be substance A, 0.9 will be substance B. So every time you move 1 unit away from the pKa, the ratio between the acid and the base will change by a factor of 10. So for example, if we were to go 1 unit to the right of 2.3, let's say 3.3, in this case, 91% of the amino acids will be in form B. The other 9% will be in form A. So at 3.3, this structure will be the dominant structure. At 9.7, we're going to have 50% of structure B and 50% of structure C. Beyond 9.7, structure C will be the dominant form of the amino acid. So that's how you can determine the dominant structure of the amino acid based on the pH. So let's say, to answer this question, what is the structure at a pH of 5? A pH of 5 will be here, which would correspond to this particular structure. If the pH was 11, we would have this form of the amino acid. If the pH was, let's say, 1, this form of the amino acid will be the dominant form in the solution. So that's how you can tell based on the pH.